Okay, the question is saying that for a two-dimensional flow, the velocity function, this is supposed to be the velocity potential function, is given by the expression phi is equal to x squared minus y squared. Determine the velocity components in x and y directions and show that the velocity components satisfy the condition of flow continuity and irrotationality. Show that the flow is physically possible and it is an irrotational flow. That is what the last question B is asking for. So, the first given velocity potential function is x squared minus y squared. And then they're asking us to find the velocity components. So the velocity potential, when you differentiate it, okay, you get the negative derivative of the velocity potential gives you the velocity in that direction, the velocity component in that direction. The negative derivative of the velocity potential gives you the velocity in that particular direction. So we just need to find this. So find now the partial derivative of this velocity potential function. So you're going to obtain, this is a 2x, and if you do that, the same thing with respect to the y, you're going to get a minus 2y. Then substituting these equations. So your velocity potential, your velocity component along the x-axis will be given by negative 2x, which is just negative 2x, and for this you get minus negative 2y, which is just 2y. So these are the velocity components. These are the velocity components. The second part is saying that show that these velocity components satisfy the continuity equation. Okay, so the continuity equation, we should show that uh, show that this is true. Okay, we should show that. So the first part, we need to find the partial derivative with respect to x, which is going to give us negative 2, and also the partial derivative of this velocity component with respect to y, we're going to get a 2. Then from here, adding the 2, if you add this x plus v y, you're going to get negative 2 plus 2, which is a 0. So this shows that the continuity equation has been satisfied. So the flow is physically possible. The second part is asking us to show that it is a rotational flow. So the flow is rotational if the velocity potential function, okay, is equal to 0. Technically, this equation and this equations are the same. Okay, let us find the second derivative of this. Second derivative, finding the second derivative is going to give us differentiate this again. We already have this as negative 2x. Okay, this is negative 2x. So differentiating this, we're going to get, with respect to x, we're going to get negative 2. Again, find now the second derivative with respect to y. This is differentiating this with respect to y. Okay, this we know already. We know it to be, it was found here, negative 2y, negative 2y, negative 2y. Differentiate it again, you get negative 2, because you're differentiating this function with respect to y. So now you add them subject to this equation, add the 2, So you're going to have plus, okay, add the two equations. This is negative 2 minus or plus negative 2, which is going to give you, which should give you, oh sorry, I made a mistake on this. This is a positive one, so this should be positive. This is positive, this is positive, this is positive. This is going to give you 2 minus 2 is 0. So since this is satisfied, then it implies that the flow is irrotational. Thank you.